This talk's going to be in 4 parts. I'm going to talk first, just a very brief introduction, and then Hugh will give a bit of a background to earthquakes and the earthquakes of 2010 and 2011 in this area. And then I'll provide a review of some of the case studies of some of the buildings that we looked at after the earthquakes. And then we'll finish off with Hugh talking about some of the testing that's been done and that we're proposing to try and get a better understanding of how earth buildings perform after earthquakes. So, just a bit of background on earth buildings in New Zealand. There's probably over 400 earth buildings that are over 100 years old. And generally all of these older earth buildings are unreinforced. They usually have rubber foundations, and some of them have performed well in earthquakes and some not so well. There's approximately 400 earth buildings constructed within the last 30 years. Generally these have reinforced concrete foundations, and generally they have vertical and horizontal reinforcement. These are some examples of the older ones, All Green perhaps being one of the most notable examples, constructed in the 1850s. It survived 3 major earthquakes in the Nelson area and is still standing, still a public building. It can be viewed. And this is a typical older cob cottage. This is one near Blenheim. This building is still there, but it got fairly seriously damaged during the Seddon earthquakes, and Doreen is involved in some reconstruction work at this cottage. This is a Sanssouci constructed in 1993, reinforced adobe, very similar details to the details in the earth building standard, even though it was built about 5 years before the standards came out. Again, a public building, you can stay here and have a meal at Sanssouci. This is a cob house built in 2003. With material directly from the site of the excavation there adjacent to the building. It's got single-storey cob walls, timber second story, and this building inside reinforced cob. It's got vertical and horizontal reinforcement. This is the King House constructed in Golden Bay in 2008. This house is on a concrete raft foundation with 6-metre deep piles. Due to the poor subsurface conditions. Again, reinforced adobe walls with vertical reinforcement and geogrid horizontal reinforcement. So background to these buildings, generally all of those recent buildings constructed in accordance with the details of the earth building standards. These were published in 1998, but a number of buildings were using some of the details incorporated in those standards. This is a typical detail from NZS 4299, showing the reinforcing details for a reinforced earth building, and that's very typical of some of those buildings we saw in those last few slides. And generally, most earth buildings in New Zealand now are constructed with these details. And here we are, just an illustration. You can see the vertical reinforcement, vertical steel, typically at the ends of the wall panels, and typically 1.2 to 1.5 metre centres. And you can see the geogrid horizontal reinforcement. These people have never done any kind of earth construction before, but could successfully build a reinforced earth wall. And we saw that in the practical yesterday. It doesn't need much previous experience, just need the right details. And there's no reason why an inexperienced builder can't build a reinforced earth wall. So I'll hand over to Hugh now.
Morning. I'm going to just give a little bit of the overview of earthquakes. And so this diagram shows some disasters, the disaster hazards worldwide, and so you get all the storms in the tropics, and you get tornadoes, and then you get these places where we get earthquakes. And this is interesting. underneath, when you get about 100 kilometers of depth, that's where you get volcanoes. Where you get a little bit back from there, you end up with these subduction zones where you've got this plate diving underneath and it grabs and then slips. And that's where you end up with the worst sorts of earthquakes occurring. And so that's what we've got in these oceanic trenches alongside parts of New Zealand and of course really bad in Chile. And so that's where we've got that going on. One of the things that we take note of is that you end up with earthquakes referenced by their magnitude. And the magnitude that we're talking about is the magnitude at the focus. And so the distance you are, both vertically and horizontally, is going to make a difference to what you experience when you experience the earthquake. And so when you look at the Christchurch earthquake, the second Christchurch earthquake was about magnitude 6.3 compared to what you had in Nepal or Chile, where we are looking at magnitude 8. Each step of that magnitude scale is 32 times the energy. And so the energy release is huge when you look at, but it's being transferred through the soil. And so you need to understand how those things work. This is just a little bit of a picture of New Zealand. At the north, we've got at the top here, we've got it subducting underneath. Down the middle, it's sliding past. At the bottom, it's subducting the other way. And so we've got this slightly complicated thing going on, and that's why we've got volcanism in the North Island and not in the south. Whoops. When we look at the Darfield earthquake that happened in Christchurch, very close to here, we ended up with horizontal accelerations in a magnitude 7.1 earthquake of 0.82 G, very close to where the epicenter of the earthquake was. And then we ended up with a surface rupture at the Greendale Fault. And so we ended up with this surface rupture expressed, and we sort of lost half a dozen slides. We will go to the first video there, please.
That's the Darfield one, correct?
Yes. So these are velocities from the Darfield earthquake. And then when we come to Christchurch, you'll notice that they die away just before they come to Christchurch. This animation is actually the result of thousands of hours of work. It has involved looking at all the borehole data, looking at the records of a number of places to calibrate this, and this is velocities. So when we're engineers, we're really interested in accelerations because we can work out forces. It also makes a difference how far things move, and that's displacement, but velocity is really easy for the geotechnical people to look at because that relates to how things translate through the soil, and they can look at the reflections, how that all works within the soil matrix. Can we go to the next slide, please?
Okay, just bear with me, Hugh.
Okay.
Somewhere around there.
so it was a totally different presentation than what I was expecting to get. We're now into the right one. Very good. Okay, thank you. Good. So when we go to our second earthquake, the Christchurch 6.3 earthquake, what you'll notice is that we have the epicenter very much closer to the centre of Christchurch, and we have this huge vertical acceleration of 2.2 G, one of the larger sort of accelerations noted around the world, and a horizontal acceleration in the Heathcote Valley of 1.4 G. Very, very high accelerations. And one of the things that we didn't talk about last time is that Mifflin's out here, and we're over here somewhere. The Darfield fault's through the middle, and okay, let's play that second. Great, thank you. Okay, so that's Mifflin and Greendale, where we saw that surface rupture, Charing Cross, where one of the houses is, and we're also, Darfield is where it's referenced for that first earthquake, and Hororata, where Richard will show you some house damage. Next slide, please. Yep. Okay, we have this as the video of Christchurch earthquake, and so here you see these massive velocities right in the heart of Christchurch, decaying away very quickly, but very distinct areas which were affected by these major earthquakes. This is work that was done by Professor Brendan Bradley at the University of Canterbury with a team of people. And back to the presentation, please. Thank you. So one of the things that's interesting about Christchurch is that you have a direction when these ruptures occur. What you've got is a piece of rock is rupturing, and it starts at one end and then it moves forward. And so you can see that as the rupture progresses, you actually end up with a piling up of these waves, and so that as we get, when you're very close to an earthquake, these sorts of effects are much more dramatic. And so this was what was seen in downtown Christchurch. And when we look at housing, when you look at Christchurch itself, we've got this area out here that had a lot of liquefaction. We had this rocky outcrop where we have high accelerations and rockfall, and there's landslides and these sorts of things. So there's distinct areas of damage in different parts of the city. This one here, the source of this rock was at the top. This is where the house was, and it went straight through the middle. In the soil liquefaction areas, you end up with the ground being shaken. One of the things with these high vertical accelerations, you end up with the ground being pulled apart and snapping back together. Really bad for liquefaction. And so then you end up with this uneven differential settlement, and this is double skin brick and veneer failures, and where the ties are just pulled clear off the brick. This is a really good demonstration of what happens when you have a 2.2 G vertical acceleration and the tiles get thrown off the house. I actually red-stickered one of these houses because there was a pile of tiles hanging over the doorway. What I didn't realise that meant was that that owner didn't get access to the house for 6 months. What we're talking about, out of plane, in plane, loadings, and when you look at out of plane loading on a building, when you're shaking pulls apart from the adjacent wall. When you're looking at in plane, what you're going to end up with is the whole wall tipping over. You're going to end up with diagonal cracking through the wall, or you're going to end up with part of the wall just sliding. And so those are the typical sorts of failures that you get with in plane. But it's generally much stiffer in plane. And so this is an overview of the sorts of damage that you get from earthquakes. And here we've got these diagonal cracks where you've got substantial panels carrying load in the in-plane direction. Here we've got this end wall that's fallen out, and we've got separation where you don't have a bomb beam along the top, and you get a corner falling out. And if you do have this in-plane strength, then where you go and have this little panel that's carrying a huge amount of load, you go and put an opening in the middle of it, you're taking away a whole lot of strength with a very, very small change. There's a bunch of other things there, won't talk about those, but this is just one cottage that was in the first of those earthquakes that Richard's going to talk some more about. You've got the corner coming off, you've got wall panels pulling apart, you've got diagonal cracking, you've got a whole bunch of these things that we've just talked about, all evident in this one house, and Richard will talk about those.
Just before you start, Richard, do I need to go back to your presentation, or is it at the end of Hugh's?
No, this is right.
Okay.
So this next part, just some case studies from our observations following first the Darfield earthquake, which is very close to here. As Hugh mentioned, that was a 7.1 earthquake, and some areas experienced very strong shaking. So this is the same cottage we saw in the earlier slide. This is the Cotton's cottage at Hororata, 0.5 G, and some classic examples of unreinforced failure during an earthquake. What was particularly interesting for me in this building was this is the first time I'd ever seen the earth wall separate from the foundation. It's very noticeable in this building. You've got a great big horizontal crack there where the earth wall is sitting on the concrete, and also all the other classic cracks you get from an unreinforced building. And here's some photos inside, so extensive damage, and really, our opinion was beyond reconstruction. And so this building was reconstructed a couple of years ago, and Bruce Forsyth's going to talk about that a bit more in one of the presentations later in this conference. This is another building we visited in the Hororata area. This is a rammed earth house constructed in 1925. Rammed earth walls. It's got a concrete foundation. It's got I think a concrete bomb beam. We're not sure if it's reinforced, but definitely a concrete bomb beam there. And considering the proximity to the fault and the epicenter, very strong shaking, it actually performed pretty well. So here's some of the background to the building. Original rammed earth building built in 1925, on-site material, techniques observed in South America. It had timber extensions, a timber second story. There's lots of vegetation around the building, so we saw damage from moisture around the perimeter of the building, and very strong shaking, 0.65 G ground accelerations. And here's probably one of the main failures in the building was the separation of the bomb beam from the top of the earth wall. So it just needed better connection there. Here's a floor plan of the building. So you can see some of the main areas of damage, but it could be saved, this building. This is another building, very close to the Green Bay Fault, about 700 meters away from this building. There was a main road there, and the center line had moved so it was in line with the outside line. So a shift of about 3.5 meters. And so this building probably 0.8 G ground accelerations, vertical accelerations similar. So very, very strong shaking. both vertical and horizontal reinforcing, had reinforced concrete foundations, timber top plate and timber ceiling diaphragm, and there's the accelerations that it experienced. Inside the building, you can see the ceiling diaphragm there, timber top plate. This photo was taken after the earthquake, so very little damage really. I think perhaps the main damage here was a little bit of movement of the lintels, 4 or 5 millimeter separation from the lintel from the earth wall, but nothing major. A little bit of a problem with this building is it had a garage attached to it, so there was some differential movement between the two buildings, and that was evident in some of the cracking at the joint between the two buildings. But again, nothing major that was any real concern. But there was a lot of cracked paving around the building, so there was a lot of very, very significant ground movement. So this is really a summary of our damage report. Immediate impression was minimal damage given the extent and severity of shaking, no real structural damage, and evidence of a lot of movement from the paving slabs and cracked tiles. And this is really the most significant damage, just a little separation of the timber lintel from the earth wall, but nothing major. And I think in any major earthquake in these sorts of buildings, we can expect similar sort of damage. This is another reinforced earthquake building. This is very near to Methven. Beautiful building, really high quality finishes, lovely inside, but a few problems with the design. So again, 280 thick walls with both vertical and horizontal steel reinforcing, detailing much the same as the standard, but the rods were only tied together, the vertical rods. They weren't joined with the couplers, they weren't welded, so really what were they doing? And there was insufficient wall bracing in the north side of the building. Only moderate shaking, but there was damage in these very narrow panels at the north side of the building because it's a very long building, and that was the only bracing that was being provided at the north side, so there was some cracking in those panels. But no other significant damage, and our recommendation was that they should increase the bracing on the north side of the building, and that could be done by adding another room on the north side and providing that bracing. This is one of the houses that we visited near Akaroa, Little River. It's supposed to have been a house with pressed brick veneer walls, and as you can see, very, very significant damage with this building. It's got pressed earth brick double skin infill panels on the ground floor, timber second story, moderate shaking, and then 7 to 6. But this was the sort of damage that we got. All the bricks falling, most of the bricks on the outside skin falling off. It was really a mess, that building. And the ties were very poorly embedded in the mortar and often had been pulled out either from the timber framing or from the wall panel on the other side. So those are some of our observations, and there was evidence of crushing of the bricks at the corners. So we visited large, probably about 20 or 30 buildings during our reconnaissance surveys after the earthquakes. But these are some of our key observations. So unreinforced historic earth buildings suffered significant damage in areas of strong shaking. Unreinforced round earth buildings, which had concrete bomb beams, generally actually performed remarkably well. The reinforced adobe buildings, which had both the vertical and horizontal reinforcing details similar to the earth building standards, they performed well. Unreinforced double skin pressed brick houses, they performed really badly. And so our main recommendations from those 2 reconnaissance surveys were unreinforced earth walls thinner than 250 and without any lateral support, really should be dismantling or strengthening those in high earthquake areas. We recommend that second stories of earth in all seismic zones be discussed damage from the second story, just so major and trying to fix later. And the other important thing is ensure adequate weather protection to your earth walls to prevent weakening of the earth wall material at the base of the walls. The earth veneer is becoming a very popular method because it's relatively straightforward. And so from what we saw at Christchurch, this is what we're recommending. It's really important to have a good connection with a nail or screw in the fixing of the ties to the brick veneer. You need to have screw-fixed ties. Nail ties are just no good. And provide horizontal reinforcing with form of geogrid for the earth brick veneer to give further strength to the veneer walls. And so in the present standards, earth brick veneer is not provided for, but we are proposing that it would be in the new standard. Okay, we'll move over to the last part, second part of Hugh's presentation, which will be about testing.
We've got 15 minutes,
Okay.
but that's pretty well known questions. So.
Okay, we can do this in 5 minutes. Okay, this is just to say that we have done a number of tests over the years. This here is just using a Proctor compaction mold, making up soil cement, and so that was what was used in a compression test. We've also used some New Zealand flakes where the fibre was extracted, cut into small lengths, made into specimens, and then that's been tested both in compression and in tension. So this is a 4-way tension test, and you can see the fibres where that is pulling apart, so we're giving some additional tensile strength to that. We've also done work with Adobe, and again the same thing here. We are looking at compression tests, looking a little bit at the aspect ratio, and we also looked at the dynamic performance. One of the things I was worried about, we do a lot of testing that's very slow, but materials behave differently for different rates of loading, so we looked at the effect of rates of loading. Actually turned out to be quite small. When we first set up the standards, we did some verification tests of the durability and validating the methods that we were using for looking at durability of the earth blocks and the test methods we were using. And then here, this is a wall that I've drawn over here in blue, where it's actually tensioned down through a rammed earth wall. We're measuring the load in the various rods in the wall, and we're sharing some load into the wall through a hydraulic ram here that's connected both to the top and to the face of the wall, and so we're transferring some load in both directions. And so this plot here is showing the wall going backwards and forwards under earthquake type loading. So that's in-plane loading for a rammed earth wall. We also did the same thing with Adobe walls, and this is a detail that was used in the earlier days where we used reinforcing mesh that was clipped. That meant that we got good bond into the Adobe, and so that's what it looked like in the wall. And again, testing in plane backwards and forwards, looking at the earthquake performance of Adobe wall systems. This is systems, not just materials, which is very important. We also put some walls on the shake table. The shake table we had was a little bit small at the time, so this is a 1/3 scale model. It's very hard to model these things and to get reasonably good results. The first set of tests we did were unreinforced but with vertical tie downs. The second set were where we put this geogrid backwards and forwards in the courses and looked at that. We have got vastly improved performance. It's actually, this is the damage, the deflections from the first one, this is the deflections from the second one. We couldn't fail it on the shake table. It didn't have enough capacity, so we ended up going and next thing that we are planning to do, and it's under construction at this very time, is looking at this idea of adobe veneers. And the thing that I'm particularly concerned about here is that we've got a lightweight framework holding a heavy veneer, and we're going to end up with deformation of the framework at the same time as we get loading on the veneer and the same time that we're pulling on these ties. And so what we're planning to do here is use that lesson of tip it over sideways, and what we can do is use an excavator, push it backwards and forwards on a hinged base so that we actually do increasing cyclic loading in two directions, and then we'll get very near the 1G horizontal on the wall. And so hopefully what we will end up doing is pouring a concrete foundation, putting down a rather large hinge, weighs 60 kilograms I think, so it can then pivot both ways on the bottom, and we're pouring a foundation, putting the reinforcement and attachments into the hinge. Then we're going to pour a separate foundation on top of that, which is what we've got here, two foundations, so we can test two walls individually. Later on we'll then be able to build a whole lintel, and the thing that is most worrying to me is the lintel situation where we're going to have some vertical deformation, out of plane deformation, and all those things working together. And so we'll validate that we actually have this veneer with a veneer inside a house. If it collapses, that's really serious. If it's outside a house in New Zealand, there's very few people that are going to be influenced. So we're particularly concerned to get this right. And so that's what we're planning, starting last week. And hopefully first test in April. On the left-hand side over there, so what we've got is this sits inside a frame, so we're held like the building would hold it, and then I can also have an independent measuring frame so we can measure the deformation of the wall, and independent